Swayam Prabha. Digital India. Educated India.
We are going to continue our discussions of systems with mass flow in this lecture. We are going to recapitulate what we have discussed in the previous lecture and look at more problems, and this time with variable mass flow. As we had discussed systems with steady and variable mass flow, examples of systems are shown which we had discussed in the previous lecture. We had derived the governing equation of motion of a system with mass flow. We had considered two time instants of the system, t and t plus delta t, when the system initially moving with velocity v having a mass m ingests a blob of mass delta mi which was moving with absolute velocity ui, and in this time going from t to t plus delta t, it ingests the mass delta mi and it throws out a mass delta mo with an absolute velocity uo. And using these two states, we had derived the governing equation of motion, which I will show you here just to recapitulate. We had calculated the moment because of this, and here this equation was, this is our master equation, and in this we had interpreted what are the flow forces at the inlet and at the exit. So, these are the flow forces which we had used in the expression of moment about a fixed point, and we had looked at the mass conservation relation and then specialized this master equation to two situations, two cases, steady systems with steady mass flow and variable mass flow. Let us now look at applications of these equations to problems. This problem again taken from Merriam and Craig's book of dynamics. This says the jet aircraft has a mass of 4.6 megagram, that means 4.6 into 10 to the power 6 gram, or 4.6 into 10 to the power 3 kilogram. And it has a mass of 4.6 megagram and a drag of 32 kilonewton because of the air, of course, at a speed of 1000 kilometer per hour. The aircraft consumes air at a rate of 106 kg per second. So, it is taking in air at a rate 106 kg per second through its intake scoop and uses fuel at a rate of 4 kg per second. This fuel aircraft is supplying, therefore, aircraft's mass is depleting. If the exhaust has a rearward velocity of 680 meter per second relative to the aircraft, determine the maximum angle of elevation alpha, which has been shown in the figure, at which the aircraft can fly with the constant speed of 1000 kilometer per hour. Here I have drawn the coordinate system that I choose, which is xy oriented with the aircraft. X has been oriented with the aircraft and y is orthogonal to it, of course. I have drawn the free body diagram and I have written down the data that is provided in the problem. Just to discuss what data was provided, the system, which is our aircraft, is taking in air at this rate 106 kg per second. So, therefore, this becomes mi dot. The aircraft spends fuel and this much mass actually gets consumed because of combustion, and then the gases are thrown out. Therefore, our system loses mass at this rate of 4 kilogram per second. Because it loses mass at this rate, therefore, m dot is minus 4 kg per second. Now, this is an important thing to notice. So, m dot is minus 4 kilogram per second because the aircraft is losing mass. Velocity is 1000 kilometer per hour. which I can convert to meter per second. The air drag is 32,000 Newton, mass of the aircraft is given. Now, relative exhaust velocity, this is relative velocity which is specified. We have to calculate this alpha max, maximum angle of elevation at which the aircraft can fly at 1000 km per hour. Now, equation of motion, I will write the master equation first, mass times acceleration of the aircraft. Now, aircraft is moving at a constant speed, therefore, this acceleration is 0. Remember one thing though, here because the acceleration is 0, that effect of m is not showing up in the equation. M is variable. Remember that mass of the aircraft is changing, therefore, that m is actually variable. Had the aircraft been accelerating, that effect of mass would have been observed, but because acceleration is 0, therefore, we are not observing the effect of the variable mass here. Other terms are as it is on the left hand side. On the right hand side are all the forces acting on the aircraft. The first force is the drag force acting in the negative I cap direction, magnitude is r. Lift force, this is not to be forgotten. Lift force is a very important force because that negates the effect of the weight, and finally, of course, the weight of the aircraft. And as before, I am reiterating what is the flow force because of the engine of the aircraft. So, that part is minus T on the left hand side, and when you bring it on the right hand side, that becomes the thrust because of the engine. In this case, the mass that is going in is not the mass that is going out. The mass that is going out is higher because fuel is being added to it. Therefore, this is a variable mass problem. The mass rate at the exit MO dot is mass rate at the inlet minus m dot. This comes from the balance of mass, and mi dot is 106 kg per second, you can see on the right, and m dot is minus 4 kg per second. Therefore, minus minus becomes plus. So, we have MO dot, the mass that exits, the mass rate that exits the aircraft system, our system is 110 kilogram per second. Velocity is 2500 by 9 I cap meter per second, we have calculated. Now, the absolute velocity of the air which is going into the system, the absolute velocity is 0 because air was stationary when the absolute velocity of air is 0, because air was stationary when it is taken into the aircraft system. So, absolute velocity of that air is 0. Now, the exit velocity UO minus V is the relative exit velocity, this we have discussed, and that is minus 680 I cap meter per second. The exit velocity is in this direction. We will use a different color. The exit velocity relative to the aircraft is rearwards. So, this is 680 meter per second, and it is in the minus I cap direction. Therefore, the relative exit velocity is minus 680 I cap meter per second, and that is UO minus V. Plugging in all these values into the master equation, I do a little bit of algebraic simplifications and look at the I cap component of the equation. It involves that sin alpha, and everything else is known, and at this instant the mass of the aircraft is 4600 kilogram, let us say. Of course, it is losing fuel, therefore, it is losing mass, but that rate is quite small. We are trying to calculate when the mass is 4600 kilogram, and if you do that calculation, alpha comes out to be 17.2 degree. Therefore, this is the maximum value of alpha at which this can fly with these parameters. Now, when the mass changes substantially, this value is going to change, of course. And from the J component of the equation, I will get the lift force, and you can plug in the value of alpha, and you can get how much is the lift force on the aircraft. Okay, that completes this problem. Let us move to the next problem, which is of a rocket. A rocket of initial mass capital M naught expels exhaust at a constant velocity v r, v sub r, with respect to the nozzle. So, this is a relative velocity of exhaust with respect to the nozzle or with respect to the rocket. The mass of the rocket depletes at a constant rate r to a final mass m b, m sub b at burnout. Burnout is the state where all the fuel has been exhausted. So, that is called the burnout. Calculate the velocity of the rocket with time and the velocity attained at burnout. Neglect atmospheric drag and variation of acceleration due to gravity. These are actually quite simplifying assumptions, I must say. This problem is again from the book of Merriam and Craig. Let us look at the coordinate system and FBT for the free body diagram, and in this case it is quite simple. The coordinate system is only the y axis vertically upwards positive. Free body diagram has only the weight of the rocket at certain instant of time and the thrust because of the ejected gases. We have to find out the velocity at any time and the velocity at burnout. Now, equation of motion, we start by writing the master equation. Now, a rocket does not take in any mass, therefore, there is no mass input to the system. Mi dot is 0, no inflow, only outflow, therefore, we have mo dot, and the force that is acting on the rocket, non-flow force, is the weight. Once again, the thrust that is being developed is because of the mass outflow. Now, from the mass conservation relation, we must have rate of change of mass of the system, which is the rocket, m dot is mi dot minus mo dot. Now, mi dot is 0, there is no intake of mass, there is only exhaust. Therefore, m dot is nothing but minus mo dot, and in the problem it specified that it is losing mass at the rate at a constant rate of r. Therefore, m dot must be minus r, the rate at which the system is changing mass, it is losing mass, that minus indicates that it is losing mass, m dot is minus r. I can integrate this and find out mass at any time. Why do I need this? Because you see in our master equation that mass times acceleration, that term survives. This is accelerating system because it is a variable mass system, that m is a variable quantity, it changes with time. That small m is capital M naught, which is the initial mass of the rocket with the fuel, of course, minus R t, which is obtained from this integration. If you integrate the mass conservation relation, then you obtain the mass at any time t, and from here I can find out the time taken for burnout, because it is mentioned in the problem that the mass at burnout, that means this is the dry mass of the rocket without the fuel, m b. The mass at burnout is m b, and from here I can calculate how much time it takes for burnout. M naught, capital M naught is specified, m sub b is specified and r, the rate at which its losing mass is specified. Therefore, I can find out the time to burnout. Now, relative velocity at exhaust, this is also specified V r, and that is in the minus j cap direction, that you can note from the figure. Y is vertically upwards positive and the jet is going with velocity V r vertically downwards. Therefore, the relative velocity at exhaust is minus V r j cap. Now, we plug in all these expressions in the equation of motion. Mass times acceleration, this is mass times acceleration in the j cap direction. Now, minus this comes from this and m o dot, right. M o dot is r, and this u o minus v is minus V r j cap. So, in all we have this term, and on the right hand side it is the weight at any instant of time t. Now, mass is depleting, this is the mass at any time t till the fuel is present. So, before the burnout has occurred, this is how the mass is changing. Remember, this equation is valid as long as there is fuel. I can integrate this equation. Velocity, it starts with 0 velocity and it attains a certain velocity at time t. T goes from 0 to some time t. I can integrate this. This integration is straightforward, and I will use the I have already used the condition that at t equal to 0 the velocity of the rocket is 0, which you can plug in and check. And then at burnout, what is the velocity? I will just put t as Tb, which I have derived here. This is time to burnout, and then I can calculate the velocity of the rocket at burnout. It turns out to be this expression, and after this time it starts with this velocity and it is a projectile in a uniform gravitational field. You can find out the height attained, etc. So, that completes this rocket problem. Let us now come to a problem with chain. Now, this is a variable mass problem. Let us discuss this problem. An open link chain of length L is equal to 8 meter with mass 48 kilogram is resting on a rough horizontal surface when end A is doubled back on itself by a force P. This chain was initially lying in this state. It was in this state initially. When this force P at this end A is applied and this double backs as shown at a certain instant after this has moved, this point A has moved a distance of x. A has moved from 0 to a distance x now, that state has been shown. Therefore, only this part of the chain is moving, only this part of the chain is moving, and this part is static at present. At this instant of time, rest of the chain is static and only the moving part is what is trailing this point A. The coefficient of kinetic friction between the chain and the surface is 0.4. So, mu k, the coefficient of kinetic friction is 0.4. The first part of the problem says determine the force P as a function of x required to pull the chain with a constant velocity of 1.5 meter per second, and part B says if the force P is constant, determine the velocity of the chain as a function of x. This statement of the problem and this figure, from this figure you should note a few things. Once again, A started from this point, and once it is pulled, you see it has moved a distance x as shown in the figure, whereas from the bent portion to A, from this bend to A, it is x by 2. A has moved a distance x, but the length of chain that has been added to this moving part is only x by 2. Right. Now, therefore, what is the, if the velocity of this point is v, if the velocity of point A of the chain is v, what is the velocity of this point? Remember, this is x by 2, because this whole thing is x, the moving part is x by 2, therefore, this must also be x by 2. Therefore, what is the velocity of this bend? Velocity of this bend is therefore v by 2. If this point A is moving at velocity v, this point, the bent portion, is moving at a velocity v by 2. Now, this has to be realized, this is an important step in this problem. Now, the coordinate system and free body diagram. Coordinate system is straightforward, it is only moving the x along the x direction. This is how I choose my coordinate system. Free body diagram has to be drawn for the moving part of the chain. Of course, this is changing, this is our system, and it is gaining mass, it is adding links. As it moves, more and more links are getting added to it. Therefore, our system is gaining mass. This is the free body diagram. It is under the action of this applied force P. There is some force because the links are getting added, which we do not know really, but there is a force which is acting, and there is force of friction. The first part of, in the first part of the problem, we have to calculate P so that the velocity remains constant. It moves, the moving part moves at a constant velocity. Therefore, in part A, V is constant. I have written out the master equation, and I have put to 0 all those terms which in the problem statement are 0. For example, acceleration, the moving part is our system, it has no acceleration, it is moving at a constant velocity. It is taking in mass, but it is not throwing out any mass, therefore, MO dot is 0, it has only MI dot. And note that this V is the velocity of the chain of the moving of our system. Actually, this is our system which is moving at velocity V, and mass is getting added at this absolute velocity. What is this absolute velocity? What is the absolute velocity at which mass is getting added? Now, this has to be done carefully. You can see there is a link which gets added to this. So, there is a rate at which this is getting added. The initial velocity of this part of the chain is 0, therefore, links here have 0 velocity, but suddenly it is getting added to the moving part, our system, and it is attaining a velocity v. Therefore, from 0 velocity, it was initially stationary, the last link at the bend, you just imagine the last link at the bend, it was stationary, on the static part it was stationary, whereas on the moving part it is moving with velocity v. Therefore, there must be some kind of an impulsive force, because velocity can change this suddenly only because of impulse, there must be some impulsive force acting, but we will not directly calculate that, we are going to calculate it through this flow force. Mi dot, the rate at which mass is being added. As I mentioned that this end of the chain is moving at a velocity v by 2. When the moving part of the chain is moving with velocity v, this bent part is moving with velocity, the bend is moving with velocity v by 2. Therefore, rate at which mass is being added is rho times v by 2, where rho is the mass per unit length of the chain. Therefore, the incoming mass rate is rho v by 2. System velocity is v I cap and v is constant. As I mentioned that this link on the static side had 0 velocity, suddenly it gets added to the moving part which has velocity v. The intake velocity, the absolute intake velocity of that link, last link on the static side is 0. Therefore, the rate at which, the velocity at which the mass is being added is 0. The absolute velocity of the link just before it gets added to the system is 0. So, ui is 0. I plug in all these expressions in my master equation. I have rho v by 2 as mi dot, this is 0 and minus v is this. So, this minus this becomes plus. So, rho v square by 2 is on the right hand side the applied force is P and the friction force, which turns out to be this. Remember, the length of the moving part of the chain is x by 2. This is an important thing to observe. When a point has moved a distance x from its starting location, so at t equal to 0, a was here, now it has moved a distance x, the length of the moving part of the chain is x by 2. Now, this I can rearrange and I can find out the force required, and I can plug in the values that are provided, and I will get the force required to keep the velocity constant. Since the system is growing as the links are getting added, therefore, with increasing value of x, this force is also going to grow, and here it is growing linearly with x, and this is valid till x goes to 16 meter, from 0 to 16 meter. Why 16? Because remember, a will move, this whole chain was of length 8 meter, and a will move from 0 to the point where this last link, this link gets added. Therefore, the whole displacement of a from its starting position will be 16 meter. Therefore, x goes from 0 to 16. Just at 16, the last link is added, and after that there is no mass addition. Just let us try to calculate, let us just try to calculate what is the force from this formula, what is the force that would be required when x is 16 meter. So, it turns out to be 195.102 Newton just when the last link is added, but after the last link is added there is no more mass addition. It becomes a simple straightforward problem of a body with fixed mass, and what is that mass, that 48 kg or 42 kg. So, that much mass of chain is moving on a rough floor, and what is the force required to keep moving it at that velocity? It is just the friction force. You have to just balance out the friction force, and that friction force turns out to be 188.352 Newton when x is greater than or equal to 16 meter. Therefore, once that 16 meter is reached, suddenly the required force to maintain the velocity drops from around 195 Newton to 188 Newton. Why? Because now that the impulsive force because of the mass addition is no longer present. It is only a constant mass system moving on a rough floor, and what we have to provide is just the friction force, and everything should be balanced because it is moving at a constant speed, constant velocity. Therefore, the force required will be just the friction force. Okay, so, there will be a jump in the force requirement when the last link of the chain has been added to the system. The second part of the question is, how will the chain move if P is constant? Again we write down the master equation. There is no ejection of mass, mo dot is 0, and here the acceleration term is there. So, m a, the first term of the master equation, is present because now the force is constant. Therefore, there will be acceleration or deceleration of the system. Mass of the system at any point of time is rho x by 2, because at any point of time after the point A has moved a distance x, the length of the system, our system is that moving part, is x by 2. Therefore, mass at any point of time is rho x by 2, and you can differentiate this also to get the rate of mass addition, which will be rho v by 2, because x dot is v. Velocity is v I cap. The velocity of a link, the absolute velocity of a link which will be added at the end of that bent part is 0, u I is 0. So, it was not moving, it suddenly starts, it gets attached to the moving part, the system, and attains a velocity v. Now, we plug in these all these expressions into our master equation. V dot is the acceleration. I have written acceleration as v dot. This is the mass at any instant when the point A has reached or traveled a distance x. This is the mass. This is because of the mass addition. This is the force. Now, this is constant force that is applied to the end of the chain, and this is the friction force acting on the moving part. Therefore, you will observe that acceleration, which is v dot, is a function of x. If I simplify this, I will get acceleration as a function of x. Therefore, following our standard principle practice, what we have discussed in kinematics, we express this acceleration, which is v dot, as v dv dx. We can write this acceleration as v dv dx. Therefore, I can write this as d dx of v square by 2, and this is what I have done, because finally this is in one dimension, motion in one dimension. Therefore, I mean this expression we have discussed previously for one dimensional motion, and here I have therefore converted the acceleration expression in terms of d dx, and I can now integrate this. If I do this integration, if I do this, so what I have done is the left hand side, by using integrating factor, I have represented in this form, and if you do this simplification, then you come to this step. Here I have taken these terms to the right hand side. These are all simple algebraic steps, and finally I can integrate and find out the velocity as a positive square root of whatever comes inside 2 p by rho minus 2 by 3 mu k g x. This is straightforward integration and using some algebra to simplify things. This is how the velocity varies with x. At x equal to 0 or 0 plus, when the force is applied, you see the velocity will be roughly under root 2 p by rho, and as it moves the velocity drops, and if p is not sufficiently large, then at some point of x, some value of x, the velocity might even go to 0, and if it goes to 0, after that the chain is not going to move. Therefore, if the chain has to move continuously till its last link is set to motion, you can calculate what is the minimum force required to make the to bring the whole chain in motion. Whole chain means till the last link. So, that you can calculate by putting this velocity. If you want this velocity at x equal to L, at x equal to 2L, because the point A moves, has a displacement of 2L. Therefore, V at x equal to 2L must be greater than 0, and with that you can calculate what should be the minimum value of P required to set the whole chain in motion. So, with that I will just summarize what we have discussed. We have again looked at the governing equations of motion for a system with mass flow, and we have discussed problems with steady mass flow and variable mass flow. With that I will close this lecture.